Thank you. Thank you, Emma, and thank you all for joining us today. We're delighted to have you here with us. So today's topic, or the first topic of this morning, is the grid integration studies, a non-friendly topic. It's specifically about understanding technical challenges and the regulatory framework. So before diving into it, allow me to leave this QR code for a few seconds so that you can scan it and submit your questions. We'll be happy to answer all of them at the end of the session. So, yeah, can leave it for a few seconds.
How's the weather today?
The weather is good, yeah. Just to fill the gap while waiting. The weather is really nice in Spain. Cool. So I think we can start. All right. So we would like to start by briefly introducing ourselves, and let me start with Enyo.
Hi everyone, thank you for joining this amazing event, and thanks to RatedPower for doing an amazing job of organizing it. My name is Gjoni. I'm an electrical engineer. I have a background in power system engineering, and for the past 6 years I've been helping transmission utilities build and maintain their network equivalent models, and also run different power system analysis and studies. Since yesterday, in a lot of presentations, I heard a lot of complaints about utilities. Today, I'd like to be their advocate, so playing the role of the devil's advocate by showcasing you some challenges that they face due to their operational needs that they have.
Happy to share the stage with you, Enyo. Myself, Jermouni, I'm an engineer with background in software development, and I've joined RatedPower a little bit over 4 years now. I've been working on different departments, from customer success to software development, and now I'm working as a product manager of the interconnection part of the product. So, let's start our presentation by briefly talking a little bit about the matrix. Just a reminder of the matrix of the rise of renewables, the typical start of presentations, but this is just to give more context to talk about challenges in the grid, and then regulatory framework, what they are and why they are so important. And then we can discuss a little bit the requirements of generators. So we would like to acknowledge the rise of renewable energy and, of course, the expansion of renewables throughout this year with our focus on sustainability and reducing our carbon footprint. This number here, you see 30% is a share of renewables in the global energy mix by 2022 worldwide. In Europe specifically, the European Union has set a target to reach 42.5% of consumption from renewable energy sources. I think we're halfway. The target is set for 2028, and the efforts needs to be doubled. The target seems a bit ambitious. However, another metric here tells us that solar by itself, the capacity of solar is surpassed 1 terawatt worldwide by 2022, and it is forecasted to be doubled by 2028. Along with this matrix as well, we have the data of the expansion of the market share, the innovation in technology, and all of these trends show us how the renewable energy actually will expand further. Of course, this rise comes with challenges, obviously, specifically for the grid interconnection. And before talking about the challenges, and maybe you could give us or tell us more why the conventional, or remind us about why the conventional energy generators do not cause the same impact on the grid, and also tell us more about the challenges of renewable energy sources.
Before starting with that, and before starting with some characteristics of renewable power sources, I want to set a common ground and make everyone understand that the power grids of how they are today, they are built and planned for the last 100 years, taking into account only like centralized generation, centralized consumption, and also they are built towards conventional power generators. So by introducing renewable power sources, these utilities will face huge challenges, especially in the transition period. So in order to showcase the challenges, I wanted to focus on some characteristics of the renewable power sources, and I wanted to point out 4 main characteristics. With the first one being variability. We all know that renewable power sources are weather dependent, so if there's wind, the wind farms will produce energy. If there's enough solar irradiance, the PV plant will inject energy to the system. And they are also like seasonal variables, so basically in different seasons, the same plant will produce different amount of energy for the same time frame. The second characteristic is uncertainty. So even though we have like very advanced and state-of-the-art forecasting tool and weather forecasting tool, we can not say with a 100% certainty how much energy we can produce in a certain time slot during the day. The third characteristic is that the renewable power sources are distributed, and we say they are distributed because of two reasons. First of all, because like these kind of plants, they are feasible in smaller scales. So basically, I'm talking here about the rooftop panels, about like PV plants that can be implemented in different commercial facilities, industry facilities, etc. So they are basically connected in the distribution grid, in the low voltage levels in the distribution grid, and also like the distributed character of them comes from the fact that they are not only weather dependent, but they are also like location dependent. So we cannot build them wherever we want. We have to fulfill a certain set of requirements to make the project feasible and to choose a location carefully in order to build these plants. The fourth main characteristic is that the renewable power sources are inverter-based. So basically they produce the energy in a DC current. In order to interface with the grid, that the grid works in an AC current, they need to have inverters in order to transform this DC current to an AC. So basically they work asynchronously with grid. So because of these characteristics, these characteristics will bring like a certain set of challenges to the utilities when the utilities will face this high penetration of renewable power sources. I wanted to group these challenges into three main categories, being like network adequacy or network inadequacy, network instability, and regulatory barriers. So basically, network adequacy is the lack of physical grid space for all these renewable projects to be to be connected and for them to inject the power to the grid. As I said before, like the grid infrastructure and the grid planning has always have in mind the conventional generators. So for utilities, it's very difficult to change their mindset and also to justify the cost of building these new big transmission lines just ad hoc for certain projects, since they need to build in remote areas. About network instability comes because of the intermittent nature of these renewable sources, so it's very hard to predict the behavior of them since they are weather dependent, so this will bring different instabilities, mainly frequency and voltage instabilities in the grid, and we will make the planning and operating process, it will bring a high complexity in those processes. We're going to talk more about network instability in the next slides and more in detail. As for regulatory barriers, so here I just want to point out one example, and I think it speaks by itself. The European network regulation for the requirement for generator took 20 years to be written and to be implemented. So this says a lot about the complexity of writing these legal frameworks that are frameworks that need to fit a lot of different markets into each one and to fit each one needs. As for network instability, I wanted to divide network instability in three main categories. The frequency stability, that's closely related to the decrease of inertia in the system. Yesterday we had a talk that was really focused on inertia, on rock-off, and it was amazing to hear that. So the inertia is a very important factor in the grid. So basically, I want to repeat that the inertia of the power grid is the sum of the inertia of all the rotating masses of the conventional generators that are connected to the grid. This inertia serves as a support for the frequency dip, for the low frequency events that happen in the grid. Unfortunately, renewable power sources, and especially PV plants, cannot give this kind of support for inertia. Wind plants can give some type of synthetic inertia, but still doesn't give the same, it doesn't have the same impact in the grid. So basically, utilities need to rely only on conventional generators to provide this type of support. And by increasing the penetration of renewable power sources, again, we decrease the level of conventional generators, so utilities face a lot of challenges with this type of instability. The second instability is the voltage one that is closely related to the reactive power output. Here I want to say that up until a couple of years ago, first of all, the technology was not there for the inverters to give like reactive power support to the grid, but also the regulation didn't force the renewable sources plants to provide this kind of support. So again, the utilities had to rely on conventional generators, and the same issue with the high penetration of renewable power sources. We have decrease of conventional generators connected to the grid, and we have lack of reactive and voltage support. The third one is output power prediction, so basically active power generated to the grid. Since we cannot predict with certainty how much energy we're going to produce during certain times of the day, this again brings complexity in planning and increases cost as well for these utilities. So these utilities need to plan better, but also like they need to increase their reserves level, especially for the primary and the secondary reserve of the system. This is highly costly for them, and they need to rely again on conventional generators in order to provide this kind of support. I can say that lately batteries are doing an amazing job, especially on the primary reserve in the VCR support, so frequency stability support for this one, but still there's a lack of VCR in every grid, and that brings the instability levels higher.
Yes, thank you for sharing, Enyo. So basically what you see here is the results of a trend report that we do on a yearly basis, where we get in touch with experts and professionals in the market, and we've asked them about what they think is the biggest challenge of renewable energy in the upcoming years. And as you can see at the top, there is the grid saturation and instability. And then comes the permits and regulation. Not only in this trend report results, but also actually if you go downstairs during the break, you will see the questions that the marketing team put up for us. And there is a question about the challenge, and you will see that we have the same results in terms of voting. We have both at the top as challenges. And this is why we wanted to highlight first the grid instability, and then we would like to talk more about the regulatory framework and to see it from a different perspective. Instead of seeing it as a challenge, but maybe see it from the standpoint of being a solution to the other challenges, namely the instability of the grid. And this is a quote that I like from Albert Einstein. We cannot solve our problems with the same thinking we used when we created them. So basically, solar and renewable energy in general, it's a transformative thinking that we have. However, in order to expand this evolution and keep it up, obviously, we need to have a fresh perspective of the challenges that this renewable energy comes with. And one of them would be to see the regulatory framework as a solution for the grid integration. So first, what are those regulatory framework and why they are important? Regulatory framework basically are requirements, or they are what defines the characteristics and compatibility of different generators into the grid. They are part of the promotions of renewable energies. They are a program, actually, of support for renewable energies. There are three types. We have the direct promotion programs, such as the feed-in tariff, subsidies, soft loans. We have the indirect promotion, for example, cutting the budget of the R&D of conventional conventional energy industry. And then comes the legal framework that comes to ensure the reduction of the barrier with the legal and technical and administrative part. So they are important not only to offer support so that renewable energy compete with the conventional generation, but also they guarantee that the grid expansion match with the penetration of the renewable energy sources. And this point for me is really important because it might lead to several consequences, one of them to capacity curtailment, and that could happen actually, which disconnects big PV plants from the grid and obviously apply losing a lot of money. That happens recently in Poland, I believe, in the last month, where there was an oversupply of generation with a lack of commitment to regulatory framework, and they end up having several curtailments and, of course, losing money. So that's also why it's important to have grid codes per region, per countries, and also per consumers versus generating facilities, but also within generating facilities to specify requirements for synchronous versus asynchronous generators. And today we would like to highlight specifically a requirement for generators, or RFG, which is applied in Europe specifically. And of course, yesterday we had a talk about regulations in Spain. So we have the RFG for Europe, but then you have specific requirements for each country again and for each type of generator. So since we're talking about renewable energy sources, we're going to focus on the asynchronous generators, and that's what Enyo will tell us more about.
Okay, so thank you for that, Sugi. So as Sugi said, we're going to focus more on like the classification of non-synchronous generators and the requirements for each of these type of generators. I want to emphasize here that these grid codes are just there to ensure that the generators connected to the European grid will fulfill a minimum set of requirements, and this is crucial in order to have like greater system stability and the security of supply. So basically, then all the European utilities can have their own set of requirements that are ad hoc to them, to their system needs. The way that this requirement for generator network codes defines the requirement is based on different generator types, and the way they define generator types is on using three characteristics: the location where these generators are connected to, the installed capacity of these plants, and also like the voltage level where these plants are connected to. So we can take an example here of continental Europe. We can see like type A generators is a PV plant from 0.8 kilowatt of installed capacity to 1 megawatt, the type B from 1 megawatt to 50, type C from 50 to 75, and type D from 75 megawatts of installed capacity and above. The third characteristic, voltage level where they are connected to, works in a very simple way. So basically, if those plants are connected to voltage levels 110 kV and above, they are always considered as type D generators, and if they are connected to a lower voltage level, then it will be the installed capacity that will define in which type they belong to. Each type of generator will have their own set of requirements, so this table emphasizes and shows that. We can see here by the types of generators, and it's clear that the generators, the facilities with the lower installed capacity will have like less impact in the grid, and they will have like less requirements to fulfill. We can see that type A, for example, generators only have like some frequency requirements for the frequency range and the low frequency sensitivity mode for over-frequency scenarios. So basically, they are required just to stay connected in the grid for certain frequency ranges. The type B generators, apart from the frequency requirements, they will have like low voltage ride-through requirements. So the same thing as frequency, they need to stay connected during certain events that will bring low voltage levels in the point of common coupling. They will also have like dynamic fault current requirements and protection coordination studies requirements. The type C has a little bit more requirements. So if you can see, they need to have like fault recorder devices. These are, for example, phase measurement units, PMUs, that will record like the voltage magnitude and the voltage angle with a high frequency in order to do like post-mortem analysis for different faults that can happen in the grid. They need to provide to the utility simulation models, like static models, but also like dynamic models, in order to showcase the different controls that they have in their system, and they are obliged to give reactive support if needed to the grid. The type D, which is the type that is connected to the higher voltage levels, but also like it has the higher level of installed capacity. Of course, it will have the most extensive list of requirements, so it will have almost all of them. We see here a couple of them, they are not mandatory, the black start and the island operation, because as we said, these are minimum sets of requirements, and then each utility can choose to have this as mandatory for their own grid or not.
Perfect. So some of those requirements are, not this slide, are we're going to be discussing them in more detail in a few minutes. But before that, I would just like to go back to the importance of the frameworks and see them from the different perspectives, from the grid and then the generating facility. As we said, there are for sure a bottleneck for the facility side or the developer side. From the grid perspective, we know that it gives or it ensures that the grid remains stable during the integration with renewable energies. It contributes to monitor the faults during or with the integration of renewables, and also it provides insights into the optimal operation. But then from the generator facility perspective or standpoint, there are also some important aspects, and we want to highlight three of them. The first is the grid compatibility, which is the one that we all know about. It helps with the compatibility with existing grid infrastructure. The modeling of the performance characteristics during different situations, in different situations. And finally, it helps catch some opportunities to actually optimize or increase the yield of the PV plant through analyzing the operational data and the performance metrics. So now we can talk a little bit more about those requirements, Enyo.
Yeah. So we can jump on the type D generator requirements, and I wanted to bring type D since it's the one that has the most impact into the grid, but also like the most extensive list of requirements. We cannot focus on all of them because it would be a 2-hour discussion about everything. So mainly I wanted to bring 3 main requirements, which are like the simulation models, for example, that these type of plants are obliged to like provide to utilities and to submit their steady state model and their dynamic model that they have. So by providing this model, the utilities will then attach this model to a broader models that they will have in their simulation softwares, and they will run different analyses, basically power flow analysis, contingency analysis, short circuit ones, transient stability analysis, and a set of different analyses that in the end will assess what kind of impact this plant will have towards the grid, and does this plant fulfill all the requirements and the operational needs that these utilities will have. So this is crucial for the PV plants and for the developers. It's very time consuming because you need to come up with the best control situation that are, I'd say, economically friendly and feasible as well. For the second set of requirements, they are really connected to the third one. So basically, reactive power management is really connected to the voltage ranges as well. This type of PV plants need to provide what is called as a reactive power compensation strategy to the utilities. So basically, they need to fulfill certain requirements based on the power factor and at the point of common coupling or the point of interconnection, that they can work within a certain range of power factor, but also in a certain range of voltage profile. Usually these compensation strategies, they are done by oversizing the inverters, by having like devices in the grid that can inject reactive power, like capacitor banks or different shunt controls. So basically all of these strategies need to be submitted and approved by the utilities. The next graph will showcase basically a graph that has like requirements for different countries regarding the active, reactive, and the power factor. Again, emphasizing that the broader requirements are just a minimum set of requirements, but then each country or each utility can have their own set of requirements based on the technical difficulties, challenges that they will have. So you can see here the example of Germany, UK, Denmark, and South Korea, that they have different ranges of power factor and reactive power that they need to provide and fulfill in the grid. So basically, the PV plants that need to that they will ask for integration within the utility need to make sure and need to provide to showcase to the utility that they can work in each of the points of the area defined by the lines. And jumping to the voltage, and again, the relationship between the voltage and the power factor. This is a very common graph that you'll see in a lot of network codes all around the world. It will differ maybe for the ranges, so the different markets will have different ranges of power factor and voltage level. What this graph means is that the power plant has a responsibility to provide a certain power factor levels in the point of interconnection for certain voltage levels. So in the case of low voltages, like 90% of the nominal voltage, they need to have a lagging power factor in the point of interconnection, meaning that they need to inject reactive power to the system in order to support these low voltage scenarios. For the high voltage scenarios, with a limit of 110% of the nominal voltage, they need to provide a leading power factor, meaning they need to absorb this reactive power in order to try to control and try to lower the voltage on those points. These are, as I said, basic. They are found everywhere, and it's very important for developers to take into account this kind of requirements during the design of their plants in order to understand like what kind of strategy they're going to use and how they're going to use and design that strategy. And by saying that, we can jump to some conclusions, I think.
Yes. Indeed. Okay, so from my side, I would like to conclude by saying that we can see the grid, the energy grid, as an orchestra with different instruments or generators. Each one has a different quality or specific quality. Some generators or instruments have a steady stream and others have a variable tempo. And the challenge is actually to harmoniously have them in order to have the right composition, let's say, as an analogy with music. But yeah, the requirements of the regulatory framework comes exactly to do that. They're important for that, to make sure that we have the right integration and interconnection. And we can actually see them as part of the solution. So in a sense, these regulatory frameworks, as I said, are not constraints. They are only guidelines to empower our evolution expansion of renewable energies. And you, I don't know if you want to share more conclusions with us.
Yeah, I think the main conclusion is like, please don't hate the utilities. They are not there to impose like restrictions for nothing. They face really a high level of challenges because of the penetration of high level of renewables to the grid. It's very difficult to operate a grid that will fulfill the needs of everyone, so the needs of the end user, the needs of different players in the market. So they sometimes can be a bit slow in doing this process, but we need to work together in order to make sure that we have a reliable and secure supply and with a high quality of supply as well.
Exactly, can't agree more. And to wrap up our presentation, I just want to remind you that our presentation was a comprehensive one. We have actually another part of it, part of grid integration studies as well, but with the deep dive into PV plant interconnection. We're going to tell you more about how the calculations are and a little bit about what we do in RatedPower in our product. It's going to be held by our colleague Alvaro Benito, same room at 12:45. So we encourage you to be there. We'll definitely be there. And thank you for listening and joining us today. Okay, so I think we have some questions, yeah? All right. What is the most important factor of instability that the renewables bring to the grid? Should we leave this question to Alvaro?
Yeah, we'll leave to Alvaro.
Okay then.
No. I think that I think we all agree that the most important factor is definitely the decrease of inertia. The frequency stability is I think the most challenging one to overcome because like it's kind of impossible for the renewable power sources to provide that kind of service. So for the reactive power support and for the voltage support, like they just need to enhance their controls within their plants. But for the inertia, it's very challenging, and we cannot get rid of 100% of the conventional generators. We need to have them or have like different tactics of having like, I don't know, synchronous condensers connected to the grid, or definitely some way of having rotating masses to provide this inertia to the grid. So I would point out that inertia for sure is the biggest challenge that we face.
Mm-hmm. And another question, is it possible to have a copy of the slides? Yeah, I think we can share them, I believe. We'll definitely share them. And then, how is RatedPower automating the grid integration processes? Well, that's why I would like you to be in the second part of the presentation with Alvaro. But yeah, to really tell you, we are actually, we currently have the reactive power management side in the software. So the users are allowed to introduce as an input the reactive power needed or required by the grid, and we size the PV plant as well as the battery system based on that. So that's from one side. We also provide almost all the parameters and results needed for the interconnection application, so that's also important. And we have plenty of other plans regarding power flow analysis and many things coming in our roadmap regarding that. Probably in the second part of the presentation you will hear more about them. Okay, are you investigating interference resonance between control systems within hybrid plants, PV plus wind and BESS, using different converters, controls, and sub-PPCs? Currently, no, we do not do that, but it would be interesting to hear more about that. So please, whoever sent this comment, that you can reach out to us afterwards. It would be really beneficial.
I would say that what we have in our roadmap are like that for sure our roadmap will come in steps, but we're going to focus more on static analysis. So mainly controls like are part of like dynamic analysis, which are much more complex, and they are not part, I would say, in my understanding, of the pre-feasibility and feasibility study. They are more part of a detail engineering phase. But again, if you have another, I don't know who wrote the question, but if you have another point of view on that one, we can have a discussion on how can we implement that in RatedPower.
Let's do that. Okay, another one. When will PV Design be able to provide power factor and voltage requirements graphs for designed PV power plants? So currently, well, in our roadmap, we're planning to enhance our calculation model so we can provide better results regarding the power factor. And that would allow us actually to give results in terms of graphs, maybe power factor in different nodes of all the systems. Those things are something that we are planning to have. But yeah, it's in our roadmap for sure.
I think that currently now we give briefly that one.
Yeah.
Just give like not the full graph, but we give the working point just for one point of the graph. Okay. So having just leading power factor, and it's definitely interesting to provide the whole graph and how this plant behaves and does it fulfill the whole graph? Can it work in every point as well? But again, whoever wrote that, please, we're very interested in this kind of enhancement, so please reach out in order to have a discussion about that.
Indeed. And another one, for Q capabilities at the POI, do you recommend installing cap banks, shut reactors, or increasing the number of inverters? That's an interesting question. Do you want to answer part of it?
Yeah, I think you're going to see that more in the second presentation. We're going to bring Alvaro going to bring some amazing use cases of that. I would say it's dependent on the market and dependent on the price of the inverters and dependent on the price of the capacitor banks and dependent on the requirements. Some markets will force you to install capacitor banks. I heard some stories of like utilities forced to install the capacitor bank on the high voltage side, which is quite costly to do so. But again, you need to make a techno-economical analysis in order to answer this question. So I would say it's depending on the case, depending on how strict are the requirements of the utility that you're gonna be connecting to. You can do that actually in PV Design very easily using the comparison tool. So you can have some sort of assumption of how the cost will be for both strategies.
Exactly. As we provide in RatedPower in the software, we provide both strategies, adding inverters or using capacitor banks. So as Ennio mentioned, you can simulate both cases and evaluate and compare. And we have another one. Can you elaborate on the instability component of voltage and reactive support requirements? I think this one is for you, Ennio.
Yeah. If we can go back.
I think we cannot go back to the slides, right?
So basically, also, or maybe like we can just leave. So yeah. I would say it's very easy and straightforward. So basically, voltage is related to the reactive power in a sense that if there's high amount of reactive power generated and low consumption of reactive power, the voltage level will rise. So we would need somehow to absorb somewhere this reactive power. So this can be done again by conventional generators or by inverters. They can work in a certain way that by keeping the active power output constant, they can work in a different side of the graph, so they can absorb that reactive power, and vice versa. If there's low production of reactive power and there's high consumption of it, we're going to have low voltage scenarios. So basically, in that case, we're going to do the opposite. These inverters or these generators or whatever other devices that are used, like capacitor bank, need to inject reactive power towards the grid in order to raise that voltage to nominal levels. I hope that answered the question.
Right, I think we don't have any other questions. So
thank you, and I hope you enjoyed.
Thank you.
Thank you both.